Since its introduction in 1962, the American CH-47 Chinook heavy-lift helicopter has been a critical backbone of combat support, carrying troops, supplies, tanks, and even other aircraft into war zones. Its capabilities as a military transport are nearly unmatched and are well known, but its surprising versatility has also seen it deployed in secret missions around the world. The Chinook has played a role in a number of classified operations, including in the daring theft of a state-of-the-art Soviet helicopter during the Cold War and in the raid to capture Osama bin Laden. It is rumored that a classified stealth version of the helicopter may have been used in the bin Laden raid, giving a tantalizing glimpse at potential Black Project upgrades that could keep the Chinook flying well into the future. In the mid-1950s, the U.S. Army began looking for a replacement for the Sikorsky CH-37 Mojave transport helicopters. Over 150 units had been produced, and the rotorcraft had not delivered the desired performance expected by the Army and the Marines. In 1957, the Army issued a formal replacement requirement for several contractors. One of them was Vertol Aircraft Company, a helicopter manufacturer based in Philadelphia. The company, originally owned by Frank Piasecki, had established itself in the market with the banana-shaped two-rotor helicopter in 1945. By the time the Army issued the request, Vertol had been developing a new tandem-rotor helicopter design, internally dubbed the Model 107 or V107 design. The rotorcraft would feature a new turbine-powered platform, which immediately attracted the Army's attention. In addition, Vertol assured the service that its V107 design could fulfill the transport duties of the Mojave with increased cargo capacity and never-before-seen speeds. In 1958, the Army awarded the company a contract to produce 3 V107 prototypes, which were then designated YHC-1A. However, after testing the model, the Army deemed the helicopter too heavy for an assault role and too light for a transport role. Even so, the U.S. Marines decided to use the YHC-1A as a tactical troop transport, eventually turning it into the refined CH-46 Sea Knight in 1962. Not satisfied with the results, the Army asked Vertol to develop an enlarged version of the same design to see if it could at least fulfill the troop and cargo transport role. The updated design was dubbed Model 114 and designated YCH-1B in 1959. A significant shift then affected the development plans in 1960, as Boeing bought the company and provided additional resources and knowledge. Even so, the Boeing Vertol YCH-1B prototype had its maiden flight on September 21, 1961, and it did not disappoint. Following the 1962 United States Tri-Service Aircraft Designation System, the YCH-1B was redesignated CH-47 by the Army. It was also named Chinook, in honor of the Native American Chinook people from the states of Washington and Oregon, and it entered service in August of 1962. The aircraft had a gross weight of 33,000 pounds, an approximate length of 50 feet, a height of 18 feet, and a width of 60 feet, but its main innovation was two 2,200 horsepower Lycoming T-55 turboshaft engines, each of which was mounted on one side of the helicopter's rear pylon. In addition, the Chinook was easily identifiable for its twin main rotor design. The two rotors were arranged as counter-rotating units, eliminating the need for a tail rotor unit. Each rotor used a 3-bladed assembly seated atop mast mountings, and the rear rotors were placed higher to prevent collision and clear the area around the helicopter for ground personnel. Besides its rotors, the Chinook was also easily identifiable due to its tubular shape. The fuselage was dotted with vision ports and featured a cargo door with a ramp at the rear, while the cockpit was located forward and provided an excellent view for the two pilots. Notably, the Chinook had a fixed 4-legged undercarriage system and could carry up to 55 armed men or over 15,000 pounds of equipment. Additionally, an external cargo hook located in the fuselage's middle section allowed the Chinook to carry additional cargo, such as supplies, artillery pieces, or even jeeps. The primary purpose of the Chinook was to ferry supplies, but it was also prepared for CASEVAC, or casualty evacuation roles, excelling as such at the outbreak of the Vietnam War. Over 160 Chinook helicopters were delivered in February of 1966 to the 1st Cavalry Division, which formed the 1st Chinook Battalion. The helicopters were given the pivotal yet dangerous task of delivering artillery pieces to remote fire bases on top of mountains, where air delivery was the only way to supply soldiers and Marines with food and ammunition. While carrying out the operations, the crewmen reduced the Chinook's maximum lift by more than 20% due to the heat and humidity of the Vietnamese landscape. Given the intensity of the firefights around fire bases and outposts, the American soldiers also improvised and mounted M60 machine guns on the helicopter's 2 forward doors to fend off Viet Cong and North Vietnamese attackers. Such a necessity led Boeing Vertol to introduce the upgraded CH-47B during the last months of 1966. The upgrades came from the demands of the servicemen and featured mountings for an M60 or M2 machine gun at the 2 side doors and 1 at the rear cargo door. In addition, more powerful T-55I-7C engines ensured the Chinook could lift as much weight as possible despite the heat and humidity. As the war in Vietnam escalated, the Army increased its Chinook fleet to 21 companies. Besides its cargo role, the Chinook also rose in importance after excelling in search and rescue, gas evac, and aircraft recovery roles. To carry out these operations, the Chinooks would usually be escorted by Cobras to retrieve men and downed aircraft located deep within enemy territory infested with hostile forces. The introduction of the CH-47C in 1967 and 1968 increased the Chinook's weight capability to over 46,000 pounds and improved its performance with more powerful engines. This made it easier for the Chinooks to retrieve downed aircraft and ferry heavier equipment to soldiers and Marines at isolated bases. 4 Chinooks were modified as gunship variants during the war and refitted with additional armor, 2 fixed-forward M2 cannons, a 40mm grenade launcher, 5 50 caliber machine guns on the sides, and 2 weapon pods for Vulcan miniguns. These gunships were effectively employed during the war, but never produced due to their elevated maintenance costs. By the time the Vietnam War ended, over 750 Chinooks had been deployed in combat. Of them, 200 were lost to enemy fire and anti-air countermeasures. Even so, it is said that during the evacuation of Saigon in 1975, one Chinook managed to carry over 147 refugees in a single lift. During the last years of the Cold War, the U.S. prepared a unique classified operation with the elite 160th Special Operations Aviation Regiment. It was codenamed Operation Mount Hope III, and the objective was to extract a Soviet Mi-25D helicopter from the African country of Chad. The Mi-25 was the export designation for the powerful Mi-24 Hind. The mission was set to begin on May 21, 1988. According to the intelligence gathered, the Soviet gunship had been abandoned at Wadi Dum, alongside other equipment, after the Libyan army, led by Muammar Gaddafi, was expelled by the Chadians. With approval from the Chadian government, the U.S. launched the operation after performing several tests, concluding that an MH-47D Chinook could successfully carry the Soviet gunship. In June, 2 MH-47D Chinooks from Company E of the 160th Special Operations Aviation Regiment arrived at N'Djamena, the Chadian capital. The 75-plus personnel quickly got to work and flew over 500 miles from the capital to the Aouzou Strip, escorted by French Mirage F-1 fighter jets. The weather peaked at over 130 degrees Fahrenheit at the site, but with the Soviet gunship firmly slung, the task force immediately left for the Chadian capital. During the journey back, a massive sandstorm forced the 2 Chinooks to fly at over 50 miles per hour to stay within visual range of each other. Once back, the Chinooks and their valuable prize were loaded into the C-5 transport, completing one of the first successful missions of the elite 160th. For the classified Operation Neptune Spear, or Osama bin Laden's raid in May of 2011, the U.S. employed 3 modified Blackhawks and 2 Chinooks. These are said to have been unique stealth variants of the helicopters, explicitly tailored for the mission. Although there is no photo or video evidence of the stealth Chinooks possibly employed during the bin Laden raid, there are speculations that they are out there, as it's believed no standard Chinooks could have been involved in the operation without modifying them for silent infiltration in a combat zone. Retired Army Chief Warrant Officer 5 Douglas Englund recounted that his Chinook was engaged 3 times by a Pakistani F-16 Viper during the operation, confirming that the helicopter was actively used during the raid. Several military analysts and engineers have sketched how the stealth Chinooks might look by applying the same modifications used for one of the crashed stealth Blackhawks. However, nothing more is known about the model, which may indicate that U.S. forces may still be employing it for secret operations around the world. The multi-mission General Dynamics Convair Model 48 Charger was a prototype for a light attack and observation aircraft designed and developed for the Vietnam War as one of its first counterinsurgency aircraft. The project was undertaken under extreme secrecy. In March of 1964, 30 engineers and production workers at the Convair facilities in San Diego, California, started working in a secluded area. That number would eventually increase to 200. When the top-secret project was finally unveiled, Convair announced it as a Light Armed Reconnaissance Aircraft, or LARA, to be used by the Marines, Army, and Air Force. Convair had anticipated the needs of the military early on, but competition from the North American Rockwell OV-10 Bronco became an unrelenting race to the skies. The Consolidated Aircraft Corporation, later known as Convair, was founded by Reuben H. Fleet in 1923. The prolific company became one of the most significant aircraft manufacturers in U.S. history, and for almost 60 years, its identity was intrinsically linked to the city of San Diego. Convair developed several notorious aircraft models, including the PBY Catalina, the B-24 Liberator, and the F-102 Delta Dagger. It also created the Atlas missile. In 1959, 2 Marine Corps developed the concept for what would later be known as a light marine attack aircraft. The idea was to build a small, low-cost aircraft able to provide close air support and operate from roads near battlefields. Then, by 1961, the Convair division of General Dynamics began exploring counterinsurgency aircraft, or COIN. A 1:6 scale model was eventually developed and tested in the Convair wind tunnel in 900 separate test runs. An amphibious configuration was also tried using a 1:7 scale model. The hydrodynamic characteristics of the float system were determined during test runs in the towing basin, both at high and low speeds and in rough and calm waters. In the last quarter of 1963, all these requirements were consolidated into a tri-service request for a light-armed reconnaissance and counterinsurgency forward air control aircraft to be used by all military branches. The twin-engine aircraft would need to carry at least 2,400 pounds of cargo, 6 paratroopers or stretchers, and have basic aerobatic abilities. It needed to operate from an aircraft carrier, fly at least 350 miles per hour, take off at 800 feet, and be capable of performing amphibious operations. Its armament specifications included 4 7.62mm machine guns, a gun pod with an M197 electric cannon, and AIM-9 Sidewinder air-to-air missiles. As America's military involvement in Vietnam grew in the early 1960s, they did not have suitable aircraft for jungle fighting. Convair anticipated this need and secretly began developing a model. The company had already designed a flight demonstration aircraft even before the request for proposal was issued. In March of 1964, Convair formally proposed its Model 48 Charger as a response to the tri-service request. At least 10 design proposals came from the major aircraft manufacturers. Work on the prototype commenced in total secrecy. The project was developed in Building 69, locked and guarded within a hangar. Employees would get access with a magnetic card and be thoroughly scanned by a security guard when going in or out. Convair started constructing the prototype as a private venture, and most personnel didn't exactly know what they were working on. Still, an entire team of engineers, draftsmen, and fabricators was mobilized. By August of 1964, the U.S. Navy announced that the winner of the LARA request was the North American Rockwell OV-10 Bronco. However, the Marines and the Air Force openly preferred the Charger, and the construction of the prototype continued. 6 months after Convair had first proposed its Model 48 Charger, the completed prototype was rolled out with the slogan, "A bird in hand is worth 2 in the bush." Even coins were printed out with the marketing slogan in September of 1964. The prototype was built to production standards in an attempt to guarantee no significant modifications during actual production. The Charger was 4,450 pounds, lightweight and compact, ready to operate in narrow and confined areas. It was a twin-boom monoplane, aluminum monocoque with a fiberglass nose, rear fuselage, and wingtips. The retractable nose-wheel undercarriage had a conventional tricycle configuration and was specifically built for a 20 feet per second rate of sink. 2 Pratt & Whitney Canada T-74 engines of 650 horsepower powered the aircraft, along with 2 counter-rotating 3-bladed propellers. A short wingspan of 27.5 feet rendered almost the entire length of the wing behind the slipstream of the propellers. This allocation increased the effectiveness of the full-span trailing-edge slotted flaps and leading-edge slats. Takeoff and landing distances were considerably reduced by deflecting the slipstream into the vectored thrust, and in-tandem seats were placed for a pilot and an observer under a sliding canopy. Simplicity and performance were Convair's main concerns. The rectangular wing and tail could easily be produced from one stamping, which reduced production costs and speed. The booms, including the vertical tail and rudder, the fuel tanks, and the landing gear, were interchangeable on both sides, providing a 48% commonality of parts, 4 times that of a conventional aircraft. All of these factors contributed to a low initial cost and improved logistics on the field. Flight controls were operated manually. They featured a large, horizontal, unique tail system and vertical tails with rudders, which functioned as directional flight controls. On the other hand, the lateral system employed combined circular spoilers and ailerons on the outboard span. In contrast, the landing gear and flap systems were operated hydraulically. For takeoff, the flaps were positioned at 10 degrees, while for landing, they turned to a full 90 degrees. The full span of the flaps and the inboard flap provided the necessary high lift required for short takeoff and landing fields. A hinged tail cone in the rear worked as a cargo bay, able to carry up to 2,000 pounds. 4 7.62mm machine guns could be mounted in pods on the sides, and hardpoints under the wings and fuselage were able to carry another 2,000 pounds of external storage, like bombs, rockets, and gun pods. The model also met the amphibious operational requirement and could be fitted with 2 giant floats. Constructed for maximum accessibility and ease of maintenance, one engine could be removed by only 2 men in the span of 15 minutes, using a simple rope if a mechanical hoist wasn't available. The Charger was a stout machine, and up to the task. Model 48 underwent extensive ground tests after its rollout, including fuel gauge calibrations, stationary engine runs, and taxiing at several speeds. The engine response was comprehensively reviewed, as were the nose-wheel steering and brakes. Its maiden flight took place on November 25th, flying from Lindbergh Field to the North Island Naval Air Station. Veteran test pilot Johnny Nebo piloted the aircraft, while the observer seat held instrumentation equipment that monitored the flight's performance and transmitted data to the ground station. The prototype was designed to take off with a ground run of 225 feet, but the operational version would be capable of speeds of up to 300 miles per hour. A 3,000-mile ferry range enabled its simple deployment from anywhere in the world. Some modifications were required after the first flight. The aircraft needed an increase in wingspan and a modified tail. But the Charger demonstrated excellent STOL capabilities with a standard payload and was awarded a 100-hour joint test contract. However, several pilots from the Air Force, Army, and Navy found the aircraft hard to control. On its 196th flight on October 19, 1965, the prototype crashed and burned in Lindbergh Field. The evaluator, a Navy test pilot, ejected at the very last minute and broke his foot when it got stuck under the instrument panel. Still, he survived. Even though the crash was attributed to a pilot error, a contract for production was awarded to North American Aviation to build the OV-10 Bronco. Convair wanted a revision, but the decision was primarily made for political reasons, and further development on Model 48 was scrapped. The Model 48 Charger would become the last complete aircraft that Convair ever built. In the 1960s, Lockheed engineer Kelly Johnson was given an almost impossible task by the U.S. Air Force and CIA. He needed to create a spy drone with range, speed, and altitude capabilities that could match the supersonic A-12. The hope was that Lockheed's Skunk Works team could build an unmanned reconnaissance aircraft unlike any other in order to replace the increasingly vulnerable U-2 spy plane. The result was the D-21. It was a ramjet with wings and a camera, built to self-destruct after its mission. Early tests were promising, but failures to execute correctly when released over China resulted in several missteps and even a Soviet clone. After Francis Gary Powers was shot down in his U-2 spy plane on May 1, 1960, President Eisenhower canceled all crewed flights over the Soviet Union. The United States was in trouble. The incident had brought the world closer to a possible nuclear conflict. Although Soviet airspace could no longer be entered by crewed aircraft, the US government needed to gather intelligence on Soviet territory. The primary goal was to use satellites to spy on the antagonistic nation, but the technology was not yet ready. The CIA decided that drones should be used until satellites became a viable option. Famed engineer Kelly Johnson, who worked on the design of the U-2 plane and the AR-71 Blackbird, was tasked with leading the team that would create the requested drone in October 1962. Johnson was the head of Skunk Works at the time, and he planned on building a long-range drone reliant on the technology of the A-12 aircraft. The Air Force and CIA required that the drone concept be capable of high speeds between Mach 3.3 and 3.5, as well as high altitude, reaching between 87,000 feet and 95,000 feet. Additionally, they required that the drone be able to travel far, with a range of at least 3,000 nautical miles or 5,600 kilometers. The hope was that strategic targets could be spied on without loss of human life, and in a more reliable way than the satellites at the time allowed. The Lockheed D-21 drone was developed as an ahead-of-its-time remotely piloted aircraft. It could carry out reconnaissance missions over enemy territory at high altitudes and at high speed. It used technology from both the A-12 and SR-71, but had a ramjet instead of the turbojet engines of the Blackbird. The plane was mostly built with titanium monocoque and a few plastic components. It had a wingspan of 19 feet 9 inches and a body length of 42 feet 10 inches. The D-21 could fly at an altitude of 80 to 95,000 feet with a speed of Mach 3.32, or 2,200 plus miles per hour. The drone carried just one high-resolution camera. However, to launch, the drone needed a mothership because of the ramjet engine, which required sufficient speed in order to function. Initially, a modified A-12 called M-12 was used for this purpose. The D-21 drone would take off from the mothership and fly a pre-programmed route while filming. Afterward, it would release the camera module for retrieval from the air or water, and then self-destruct to prevent enemies from reverse engineering the technology. Naval ships would be positioned to retrieve the camera module from the water in case the Air Force aircraft failed to retrieve it from the air. The D-21 was first tested thrice from the M-21 Blackbird. These tests all went fantastically, showing real promise. Unfortunately, the fourth try was haunted by the drone experiencing an asymmetric start as it went through the bow wake of the M-21. As a result, the drone crashed into its mothership mid-air. The crash happened at the incredibly high speed of Mach 3.25, and although both pilots were able to escape, one of them was lost at sea. Following the disaster, Lockheed abandoned the M-21 mothership project. They opted instead for placing the drones under the wings of the B-52H bomber. The choice was positive for the development, but the 2 modified A-12 launch planes and the 20 drones built had totaled a cost of $440 million, adjusted for 2019. Several failures followed, but Lockheed trod on and successfully launched the first D-21 flight from a B-52H in June of 1968. Soon after, the program was ready for operational espionage flights over China. The launches of the D-21 from the B-52H planes was established under a classified test program called Tag Board, with the drones themselves being called Project Super Bowl. In a 1969 memo, the Joint Chiefs of Staff explained their expectations for the program. Quote, "The Tag Board drone provides a unique technical capability to satisfy national requirements to conduct imagery reconnaissance operations against targets hostile or potentially hostile to the United States." The D-21 was primarily targeted at spying on Chinese nuclear sites. China had tested an atomic bomb in 1964 for the first time, and the intelligence community was deeply vested in learning about the progression of Chinese nuclear technology and capability. A total of 4 missions were launched to spy on the facilities in southern China that satellites had failed to supervise sufficiently. Another Joint Chiefs of Staff memo from 1969 stated, quote, 93% of the high-priority South China targets had no coverage during the previous 2 months. While they acknowledged that China may be able to detect the drones through radar, they believed that Chinese missile systems would not pose a tangible threat to the project. Still, the flights were incredibly unsuccessful. 2 drones were lost, 1 was unable to eject the camera module, and the last returned irretrievable footage. On the 3rd try, in March of 1971, the drone completed the journey. Still, according to the National Reconnaissance Office, quote, "The parachute system was partially disabled by loss of the air pickup chute, which prevented an air snatch by the JC-130 aircraft. There's a strong probability that a malfunctioning valve prevented adequate cooling of the parachute compartment during flight of the drone. The resultant overheat condition, sustained for over an hour, could have degraded the tensile strength of parachute components." Although the flights over China were an absolute failure, the program provided early insight into the use of drones. The technology was almost unthinkable at the time, and the altitude capabilities of the drone are impressive even by 2020 standards.
After the failures, National Reconnaissance Office Director John McLucas wrote in an April of 1971 memo, quote, "I've become increasingly convinced that we should be expending our efforts on upgrading our satellite activities, rather than trying to continue with air-breathing vehicles. Drones, deemed unsafe and unreliable, were cancelled on July 15, 1971, with the converted aircraft returning to their regular operations." The US Air Force accidentally sent the Soviets a gift with the first D-21 launch. The cutting-edge drone was conducting its reconnaissance mission over Chinese nuclear sites and failed to turn around correctly. It ended up crashing into Siberia. The Soviet Union rescued the wreck, and according to aviation historians Yefim Gordon and Vladimir Rigamont, quote, "Many leading enterprises and organizations of the aircraft, electronic, and defense industries were commissioned to study the design of the D-21, together with the materials used in its construction, its production technology, and its equipment." The Soviets then commenced work on the Voron project. They designed a supersonic drone for strategic reconnaissance based on American technology. The drone was planned for launching from the Tu-95 or Tu-160 bomber aircraft. Once the drone took off, a solid fuel booster would accelerate it to supersonic speed when the ramjet would have turned on. After following a pre-assigned flight schedule using inertial navigation, it would return to base. The film canister would land by parachute, and then the drone would land rather than self-destruct. Unfortunately for the developers, the project never moved from the design stage because of the promise shown by satellites. Unlike drones, satellites could not be shot at or captured by the enemy. In the mid-1980s, the United States received confirmation of the Soviet capture when a KGB agent turned over a metal panel from the D-21 to a CIA employee. Due to the ever-pressing concerns of the Cold War, the US military strongly considered converting the D-21 drones into unmanned strike craft. Under this tentative plan, the US Air Force would have used the D-21 as high-speed, deep-penetrating bombers capable of delivering nuclear weapons. In a January 1971 memo from the director of the NRO, John McLucas, directed to the Deputy Defense Secretary, McLucas stated, quote, "With respect to your question about whether tag board should be considered as a drone or bomber, we've done some investigation and discussed this with the Air Staff and SAC. I will be glad to do any additional analysis or other work which you might suggest." The idea of using a drone for nuclear bombs was attractive, as it seemed like a viable weapons platform, especially since issues had popped up with other weapons delivery systems. By the end of the 50s, it was clear that strategic bomber aircraft such as the B-52 were vulnerable to Soviet defenses and fighters. Therefore, the Air Force had to work on developing an air-launched ballistic missile, the Skybolt, and on a cruise missile, the Hound Dog. The Skybolt was delayed in testing, and President Kennedy decided on canceling the program to focus on Polaris ballistic missiles and Minuteman intercontinental ballistic missiles. The Hound Dog missile, however, did enter service in 1960 and was retired in 1978. Still, had the D-21 been armed, it would have had 3 times the range of the planned Skybolt missile with greater speed. The range would have allowed the military to target Moscow, for example, from the middle of the North Atlantic Ocean. The Air Force toyed with the possibility of either having it carry a single warhead or several bombs that it could drop along a route. Not only was the technology promising for long-range attacks, but also for short-range ones. The drone could have flown close to a target area during a potential crisis, inspiring deterrence regardless of whether it actually launched an attack. They would also be easier to recall than a ballistic missile should a mission be aborted. Unfortunately, the failure of the M21 mothership project and the subsequent failures in China meant that the unreliability of the drone also killed any future talks about using it as a weapon. Few people outside of the chain of command and Lockheed were aware of the drone's existence. The public only became aware of it once a couple of models were placed in the Air Force's storage and disposition facility at Davis-Monthan Air Force Base towards the end of 1976. By then, the D-21s were in the process of being retired. Some of these drones survive in American museums, and one of the self-destructed wrecks was put on display in Beijing after Chinese authorities located it. The details of the program were not available to the public until March 21, 2019, when several of the tag board documents were declassified. The X-20 Dinosaur may be the greatest space bomber that never came to be. This single-pilot reusable spaceplane was envisioned to reach the Earth's orbit and glide across long distances until it landed unpowered on a runway. This would have resulted in an aircraft that could have been able to engage in an intercontinental nuclear strike mission, or fly undetected in reconnaissance missions. The Dinosaur was conceived after decades of research by pioneers in liquid propeller rockets and hypersonic flight, much of it initiated by Germany during World War II. These men dreamt of a plane that could take off from Germany and bomb the US in a matter of hours. Years later, with the German scientists now on their side, the US Air Force expected to use the Dinosaur as a weapon against the Soviets. During the plane's development, astronaut Neil Armstrong became a key figure in figuring out how pilots could eject the glider if the rocket ever exploded. The project was far more advanced than other human spaceflight missions of the time. Still, despite its promise, the project was brought down by politics. The dinosaur never had one specific objective, and no other benefits could be found for military purposes, at least publicly. Hints of the design lessons learned from the X-20 can be glimpsed in DARPA's secretive X-37 that's orbiting the Earth today. Austrian Eugen Zanger, an expert in liquid-propelled rockets, dreamt of a future in which commercial flights could travel the upper stratosphere and reach the opposite side of the world in an hour. In the late 1930s, Zanger and mathematician Irene Bredt came up with the concept of the Silbervogel, a rocket-powered suborbital bomber for the German Luftwaffe. The bomber was meant to launch from Germany, attack New York, and land in the Pacific Ocean. For this, it would fly in short hops and then fire up a rocket engine climb to an altitude of 90 miles. Then it would soar down into the stratosphere and be lifted by air density. The Silbervogel was never produced because of its complexity and cost. Still, the concept paved the way for the development of the first spaceplanes. After the war, German scientists Walter Dornberger and Kraft Erika were brought to the US in Operation Paperclip, and they began working for the Bell Aircraft Corporation. They developed the Bommy, a rocket-powered vehicle similar to the Silbervogel, but with a vertical launch. The prototype was envisioned as an aircraft useful for research and reconnaissance. Eventually, the Bommy project was separated into 3 programs. One of them was Project Highwards, which was focused on hypersonic weapon research and development. The programs were later consolidated and came to be known as the Dinosaur Project. It was also a successor to the X-15, a hypersonic rocket-powered aircraft. It was in October of 1957, just days after the Soviet Union had launched the satellite Sputnik 1 into orbit. The National Advisory Committee for Aeronautics, NASA's predecessor, held a convention in California to discuss the future of high-speed flight research. The U.S. Air Research and Development Command proposed a 3-phase program to create a vehicle that could carry out bombing and reconnaissance missions. This rocket-powered prototype would be boosted into the sky at nearly escape velocity and enter an exo-atmospheric trajectory. After it re-entered the atmosphere, it would bounce or glide upwards with its lifting body and wings. The nickname Dinosaur was selected as a reference to the dynamic soaring landing profile of the project. The first stage would develop a research vehicle. The second would focus on reconnaissance. The third stage would create a bomber version of the spacecraft. It was expected that the Dinosaur would carry out its first glide tests in 1963. The aircraft with a functioning weapon system was to be shown in 1974. The plan was to launch the Dinosaur from Cape Canaveral in Florida. In 1958, 13 companies competed for the project's contract. Bell had been working on similar designs and research for 6 years, which made the company a pioneer in the subject. But the contract was granted to Boeing thanks to their concept of passively cooled structure. The partnership of Martin Bell was assigned to build the booster. Still, after the contract, there was considerable uncertainty about the purpose of the Dinosaur, as the priorities shifted from military applications to suborbital hypersonic flights. As the project evolved, the vehicle was seen as the potential first spacecraft of the United States. Such uncertainty was evident in the project's X-20 designations. Even though X-planes are used for testing and experimentation, there was hope that the Dinosaur would drop atomic bombs from low Earth orbit. The original design by Boeing was modified until it looked just like the glider proposed by Bell. Unlike jet fighters, the Dinosaur had a round shape to withstand the shockwaves during liftoff and landing. Since regular wheels would catch fire during re-entry, retractable wire brush skids were developed by Goodyear to allow the plane to land on any runway. Its hypersonic lift-to-drag ratio enabled it to divert from a planned landing and still be able to land anywhere between Alaska and Ecuador. The design became increasingly heavier until reaching a range between 8,000 and 11,000 pounds, depending on the configuration. It had a wingspan of 20.8 feet and measured over 35 feet in length. And because it was 3 times as big as other space capsules at the time, a larger launch vehicle was required to boost it. The X-20 had a clean and functional cockpit for a single pilot, with an equipment bay located behind it, which could be adapted to fit an extra passenger. In total, the dinosaur could carry up to 10,500 pounds at launch. Trying to design a powerful enough booster led to many complications and delays for the program. The Titan I and II used the same rocket engines as the X-15, but were insufficient to lift the dinosaur off the ground. Eventually, the Titan III, equipped with 2 upgraded 10-foot diameter motors, was selected as an adequate booster that could carry the dinosaur into low Earth orbit. Plans called for the glider to remain attached to the Titan III until it reached orbit. Then, complicated maneuvers would have been required to change its orbital inclination. The positioning meant that enemies would have a hard time tracking the spaceplane's overflight path and time, making it a powerful tool for bombing and reconnaissance missions. It was also planned that the spaceplane could rendezvous with satellites and potentially pursue enemy space-based targets. As the project evolved, the dinosaur was not considered a spacecraft because it would only skip along the atmosphere. Therefore, the design didn't prioritize its capability to become a fully orbital spacecraft. The X-20 would be flown through manual controls and automated augmentations. Inside the cockpit, pilots would find all the instrumentation, life support equipment, and an ejection seat that only worked at supersonic speed. Although the cockpit was considered functional and straightforward compared to other spacecraft, it was still filled with round dials and switches. The spaceplane would face extreme temperatures due to its ability to reach hypersonic speed, and the friction it would face when re-entering the atmosphere. It was theorized the wing's edges could reach 2,822 degrees Fahrenheit, and the nose cap over 3,632 degrees Fahrenheit. The dinosaur structure was made of a Rene 41 superalloy, a nickel-based alloy that could withstand temperatures up to 1,800 degrees Fahrenheit. Heat-resistant ceramic tiles and other alloys were used for the leading edges. The nose cap was protected with zirconium. Meanwhile, internal compartments had water walls that provided passive cooling and greatly diminished the structure's temperature. Researchers were constantly challenged by the design of the spaceplane. But according to Richard Hallion, former Air Force chief historian, the dinosaur was, quote, a might-have-been that never displayed insurmountable flaws. Since the dinosaur was to be piloted by a human, special considerations had to be made to guarantee pilot safety. Neil Armstrong was one of 7 astronauts selected in secret to fly the dinosaur in April of 1960. He was brought into the project to develop an effective abort technique in case the rocket exploded during launch. Ejection was considered impossible because the dinosaur's nose would be facing skyward, leaving the pilot on his back. Another caveat was that the pilot would only be 100 feet above the ground during launch. If the pilot ejected laterally, he would reach the ground before the parachute opened. Armstrong concluded that the only solution would be for pilots to shoot the engine and fly to a safe altitude. Then they could glide down and successfully land the aircraft. Armstrong set out to prove his theory aboard a Douglas Skylancer, which simulated the dinosaur's aerodynamic characteristics. During the test, Boeing reproduced the runway and launch pad at Cape Canaveral, where the dinosaur was expected to launch. Armstrong flew the aircraft over the mock launch port and entered into a steep vertical climb. When Armstrong reached 8,000 feet, he rolled the plane over to glide and land safely. His theory proved correct, but he later admitted to being glad he'd never had to try it on the actual dinosaur atop a rocket. In 1962, Armstrong left the program to join NASA's astronaut corps and eventually became the first man to walk on the moon. In total, the simulated X-20 accumulated over 8,000 piloted hours. During simulated test flights, significant breakthroughs were reached in high-temperature material research, and parts of the airframe were already being fabricated. Despite its promise, however, the project lost momentum and the Stage 3 bomber design was cancelled in 1963. Next, the program's military reconnaissance version was cut, and the Dinosaur development shifted to only focusing on orbital research. Its ending designation of X-20 meant it was to be an experimental vehicle that would never see large-scale production. At the same time, the Dinosaur was also facing extreme competition from NASA's Mercury program. Ballistic re-entry space capsules proved far more efficient for the purpose of space exploration. In December 1963, Secretary of Defense McNamara cancelled the Dinosaur before it ever got a chance to fly. The vehicle had cost an investment of nearly $400 million, but had no clear scientific mission or benefit for the military. The same day the project was cancelled, the Air Force announced the Manned Orbiting Laboratory. This new program called for a single-use space station to house a crew of 2 astronauts to live in for 40 days. The laboratory, which explored the utility of sending people to space as part of military missions, was also cancelled. After the Dinosaur, the Air Force developed other spaceplanes like the Prime, Asset, X-23, and X-24. But by the time the Nixon administration came along, the Air Force had to participate in the Space Shuttle program and paused to develop its own designs. Had it flown, it is possible that the Dinosaur could have become a supply shuttle or space taxi. Instead, the idea of a small spaceplane didn't reappear in public until the launch of the secretive unmanned X-37 in 2010.
The Panavia Tornado was the first Royal Air Force aircraft to be fully designed for the digital age. Equipped with highly complex automated systems, the type had a remarkable advantage in electronic warfare and could easily jam or deceive enemy defenses. However, the strike attack aircraft was initially conceived as far back as the 1970s, and it could carry either conventional or nuclear weapons and operate far and wide throughout Europe at an extremely low level. With such state-of-the-art features, the Tornado quickly became one of the most advanced ground attack aircraft of its time and provided the Royal Air Force with a cutting-edge frontliner that was still creating havoc at the turn of the century. As the 1970s approached, the need for a quicker and more versatile bomber than the Vulcan became the priority of several European nations. The United Kingdom had recently cancelled the TSR-2 and subsequent F-111K aircraft, and as Richard Fairclough, a design engineer at British Aircraft Corporation, said in an interview, quote, "The overall organization and management of the Tornado project did learn an awful lot from TSR-2. Not so much what to do, but what not to do." The primary objective of the new endeavor was to create an aircraft capable of undertaking missions in technical strike, reconnaissance, air defense, and maritime roles. Many nations were initially interested in the project, including Belgium, the Netherlands, and even Canada. However, only 3 ended up participating. The United Kingdom, West Germany, and Italy soon formed a consortium known as Panavia Aircraft GmbH, which consisted of British Aerospace, MBB, and Air Italia. Their engineers and designers studied several concepts for the multi-role combat aircraft, or MRCA, including alternative fixed-wing and single-engine layouts, before coming up with the final airframe. As a multi-role warplane, it was planned to replace several types of aircraft in the different air forces it would join. At the time, the Cold War demanded an aircraft capable of fielding strategic weapons that could be dropped with precision. Still, as Roland Beaumont, director of test flying at British Aircraft Corporation, put it, quote, "The whole policy of the program, whether it was right or wrong, was appeasement rather than confrontation. I think that probably is the only way you can do it in international collaboration." Having said all that, the Tornado was worked through. It had its difficulties in development, but it turned out to be a brilliant operational aeroplane. During the Cold War, Western powers envisaged one main mission for their aerial fleets: the delivery of conventional and nuclear ordnance to the invading forces of the Warsaw Pact countries of Eastern Europe. As such, the new MRCA was intended exclusively for low-level strike missions, hoping that it would be a viable threat. As part of the requirements, the Tornado had to have solid high-speed and low-speed flight characteristics that would enable it to perform as a low-level supersonic strike aircraft. Hence, the aircraft adopted a variable sweep wing instead of a typical swept or delta one. The idea was not new. During the 1960s, aeronautical designers explored the concept of merging the maneuverability and efficient cruise of straight wings with the sheer speed of swept back wings. It could be said that its purpose heavily influenced its design. Moreover, the Tornado significantly differed from its predecessors in its multi-role versatility and more advanced systems in avionics, with its then groundbreaking fly-by-wire system that facilitated the pilot's workload and eased control. The first Tornado variant, the Interdictor Strike Fighter bomber, was the first European military aircraft to be equipped with the then innovative fly-by-wire flight controls. Chief Test Pilot Paul Millett remembered the new flight controls as, quote, the biggest new thing. He then added, quote, it was a big step in the dark controlling aircraft purely by electronics. When you want to go high speed, you sweep the wings back. That reduces the frontal area, and you can go much faster. It also improves the gust response at low level. With the wings fully swept, you can charge along at quite high speeds and not feel a thing. It is an extremely good low-level attack, without any doubt at all. The first development aircraft flew on August 14, 1974, at Manching, Germany, with Millett at the rudder. Afterward, he expressed, quote, aircraft handling was delightful. The actual flight went so smoothly that I did begin to wonder whether this was not yet another simulation. Still, the test revealed the need for minor modifications, and the contract for the first batch was signed on July 29, 1976. The first deliveries to the Royal Air Force and German Air Force started in June of 1979, and the first production aircraft flew on July 10th. However, the first Italian Tornado was not delivered until the fall of 1981. The standard air vehicle approach yielded the logistics, training, and cost benefits of a single aircraft type, and a family of mission variants soon branched out. Such models were optimized for different roles to keep the combat effectiveness of a range of specialized equipment. The core version, the IDS, was designed for ground attack, but it retained anti-shipping and reconnaissance capabilities at extremely low altitudes. Beaumont explained, quote, the Tornado IDS was designed as a specific one-task low-level strike airplane, with the additional capability of elaborate advanced reconnaissance. Therefore, its philosophy was of high wing loadings, tough structural strength, very fast low level, and nobody worries too much about what goes on with the altitude. The version used by the Royal Air Force was designated GR-1 and later upgraded to GR-4. Germany and Italy kept the IDS identification. Meanwhile, the UK advocated for a specific need to defend large stretches of airspace in the north and focused on securing excellent endurance capabilities, as well as improved standoff air-to-air missile armament. In response, Panavia developed a specialized fighter version for long-range interception, the air defense variant, designated F-3. As for Germany and Italy, they developed another version specifically for reconnaissance and the location and suppression of enemy anti-aircraft systems. Germany formulated the requirements in the early 1980s, and within a decade, the Tornado ECR, or Electronic Combat and Reconnaissance, was created. The new variant retained the capabilities of the older IDS, but received upgraded electronic warfare equipment, more suitable for the new millennium. Early in its service life, the Tornado carried nuclear weapons to use against Soviet bloc forces. However, those weapons evolved from freefall to more sophisticated ones over the years. Cleared to carry the majority of air-launched weapons in the NATO inventory, the Tornado could convey unguided and laser-guided bombs, anti-ship and anti-radiation missiles, and many specialized weapons such as anti-personnel mines and anti-runway munitions. For added survivability in combat, the MRCA had onboard countermeasures like flare and chaff dispensers, but also electronic systems like underwing pods. In contrast with some American aircraft like the F-14 or F-111, the Tornado featured mechanically attached hardpoints on its wings. Then, as the wings swept back, the pylons rotated, and the weapons kept facing the direction of the flight, regardless of the degree of the sweep. In addition, the aircraft incorporated a combined navigation and attack Doppler radar that conducted simultaneous scans for targets and fully automated terrain following for level operations. Its all-weather, hands-off, low-level flight capabilities were indeed one of the Tornado's core advantages. The cockpit housed a crew of 2, a pilot in front and a navigator in the rear. While the pilot took the air vehicle to any given destination, the navigator behind him called the way. At first, he consulted a lot of maps, but it was later upgraded to cassettes plugged into the cockpit. As such, the navigator position morphed into a weapons system operator. Chief designer John Waite later recalled, quote, "He said, right, well, we've got to get rid of some of this fuel, so we can either dump it or we can have some fun. So we whipped up into the Yorkshire Dales, and he said, now I'll show you the terrain following radar. He picked the Dales, going across them, and he stuck it into hard right at something like 400 knots with a 100-foot clearance. All it was rocks, heather, rocks, heather, rocks, heather, sky, rocks, heather, rocks. That's all I could see in front, and he was sat there in the front cockpit with his hands on his head. So I mean, this was Tornado at its best. It really was." The Tornado had a distinguished operational history. With its original desert pink paint, the GR-1 Foxy Killer flew more bombing missions than any other RAF Tornado during Operation Granby in 1991, conveying huge JP-233 runway denial weapons. 2 decades later, the more advanced GR-4 served in Operation Ellamy in 2011, enforcing the no-fly zone over Libya, while flying from bases in Italy. The improved version was armed with the Brimstone launcher, which enabled it to hit individual targets like soft-skinned vehicles with each missile. Despite being initially designed to carry nuclear weapons, the Cold War-era aircraft ended up serving in modern conflicts like Afghanistan, Yemen, and Syria, as well as Bosnia and Kosovo. Notably, the Royal Saudi Air Force became the only export operator besides the original. Overall, 990 aircraft were built across all variants, and the RAF retired the legendary aircraft in the spring of 2019 and celebrated it with several special performances. It was then replaced by variants of the Eurofighter Typhoon. Ultimately, the Tornado was the backbone of the Royal Air Force for the best part of 4 decades, always on the front line, wherever the air service went. After years of hard work, the Soviets managed to finally perfect an innovative aircraft that could hover like a helicopter and fly like a fighter jet. From the start of the Cold War, they had strived to take the leading edge in military technology, and with the help of renowned aeronautical engineer Alexander Yakovlev and the impressive Yak-141, they almost did. The remarkable machine boasted 4 prototypes and broke several world records, but the fall of the Soviet Union cast a spell over its potential use. In a twist of fate, it would be the Russians' most loathed enemy that would eventually benefit from their own notorious technology. For decades, vertical takeoff and landing flight of fixed-wing aircraft troubled aeronautical engineers, as the military applications of such versatile machines promised a myriad of new opportunities. At the peak of the Cold War in the 1960s, several models and sketches were fashioned, of which the most famous was arguably the British Harrier, both in its land-based and navalized forms. On its part, the Soviet Union created the Yakovlev Yak-36 freehand, and 4 prototypes propelled the Soviets' engineering forward. The Yak-38 Forger eventually entered production and served with the Soviet Navy with over 200 examples. Nevertheless, the model was limited in its ordnance-carrying capabilities, not to mention overall performance. In truth, the Yakovlev aircraft designer and manufacturer always considered the Yak-38 an interim aircraft, or a mere step in the development of an actual military VTOL aircraft. Even before its creation, the Soviet Navy had explicitly requested a piece of machinery more capable than the eventual Yak-38. Still, the Navy issued a contract to Yakovlev in 1975, demanding an aircraft with a single mission: air defense for its fleet. The new model had to expand the capabilities of the Yak-38, and unlike its predecessor, sustain supersonic speed. Moreover, it was expected that its deployment would be similar to frontline fighters in terms of maneuverability, agility, radar, and weapons loads, as well as ranged interception. A new program was thus born, under the designation Product 48. Soviet aeronautical engineer Alexander Yakovlev was especially concerned about the project because of its importance and complexity. Thus, he assigned a significant portion of his Experimental Design Bureau, or OKB, to the development of the new aircraft. For the Navy, it would be the beginning of a new era of fighter aircraft, but for Yakovlev,
it was an opportunity to design fighter aircraft again. No less than 10 chief engineers worked simultaneously on the project that the military secretly called Yak-41. Over 50 different designs were considered, but many displayed incompatible engine arrangements and considerations. Most importantly, the challenge lay in providing supersonic performance and managing to keep a vectored thrust capability simultaneously. As a result, engineers adopted a single-engine layout, both safe and simple. With a key necessity for an afterburner, twin-engine designs were abandoned, as an engine loss during landing would cause an immediate roll to the side. Hence, a single vectoring nozzle behind the center of gravity was settled as the best possible arrangement. In addition, dedicated vertical thrust jets were positioned behind the cockpit, and general forward thrust and lifting were provided by a jet pipe at the rear designed to turn down to 90 degrees to provide extra support for VTOL maneuvers. Notably, that same arrangement can be found in modern American F-35s. The Soviet engineers developed an airframe around the single-engine concept, and considerable time was spent on the development of another characteristic feature, the flat, rectangular nozzle. The design proved adaptable to the drastic changes in the configurations required for thrust vectoring and supersonic flight, and it also allowed for a thin and shallow tail. However, a circular nozzle was employed in the end. It was fitted in between twin booms, which in turn supported the distinctive twin-fin tail, straddling both sides of the engine installation. The remaining sections of the Yak-41 mimicked previous design lines of Soviet high-speed aircraft, such as Mikoyan-Gurevich MiG-25s and MiG-31s. Its airframe featured a slab-sided forward fuselage with rectangular intakes at both sides of the cockpit, and its small-area wings were clipped at the ends, and profiled a marked sweep along their leading edges. Furthermore, the wings could be folded to aid in carrier storage. Likewise, the undercarriage was retractable on top of being reinforced and equipped with multi-disc anti-skid brakes. The steerable nose wheel retracted to the rear, while the tricycle main gear retracted forward. Meanwhile, excessive heat from the engines emitted during landing was expected to damage the fuselage, so key parts were manufactured in titanium and non-critical ones were completed with composites or graphite. What's more, hovering time was limited to 2.5 minutes to avoid overheating. Ultimately, the design included a 3-engine layout controlled by an interlinked digital system, which could in turn control engine startup as well as modulate thrust during vertical flight. 8 spring-operated dorsal flaps provided the engines with air, while the exhaust exited downwards towards the belly and out through an opening covered by 2 ventral doors. The primary forward thrust and lift unit was a Soyuz R-79V300 turbofan engine, capable of 24,300 pound force on dry thrust and 34,170 pound force with an afterburner, while the lift engines were RKBM RD-41 turbojets, which provided 9,300 pound force of thrust each. In addition, twin tandem reaction control jets were fitted at the wingtips, and a swiveling yaw jet was placed under the nose. As for the cockpit, it was pressurized and air-conditioned. The canopy was bulletproof at the front, and although it hinged to the right, a long dorsal spine blocked the rear vision. The seat was installed with automatic ejection in case the engine duct rotated past 30 degrees with an airspeed lower than 186 miles per hour. The Yak-41 prototypes were equipped with simple instrumentation, very similar to the previous Yak-36M. Nevertheless, production aircraft would have featured an extensive avionics and weapons suite, with Doppler radar and laser TV ranging and aiming. Moreover, a heads-up malfunction display, or HUD, would be connected to a helmet-mounted missile aiming system similar to the MiG-29. Such a system would have allowed pilots to lock on to enemy aircraft by turning their heads up to 80 degrees from the front. Being a combat aircraft, production-quality Yak-41 models were slated to carry a 30mm GSH-301 internal cannon for close work, fed by a 120-round cassette. For external storage, 5 hardpoints were included, 2 under each wing and another on the center line. They would carry air-to-air missiles of up to 5,735 pounds in total, in different combinations of short, medium, and long-range projectiles. Yakovlev was able to fund 4 prototypes, the first of which was known as 48-0 and was a bare airframe for routine static and fatigue testing with no callsign. The second model, 48-1, was a non-flying testbed with callsign 48. Only the final 2 prototypes, 48-2 and 48-3, with callsigns 75 and 77, would be flight tested. Furthermore, only the airworthy models would be painted all gray with a black radome and fin cap antennas. The The series' first flight happened on March 9, 1987, with 48-2, and its first hover was successfully attempted 2 years later, on December 29, 1989, with 48-3. Then, on June 13, 1990, the last prototype achieved the first complete transition from vertical to high-speed flight to vertical landing. And finally, the first vertical carrier-based landing was accomplished on September 26, 1991, aboard Admiral Gorshkov. During the testing phase, the aircraft was considered in excellent shape regarding combat maneuvers. What's more, test pilot Sinitsyn set a dozen world records using the Yak-41. However, such designation was still top secret at the time, so the model became known as the Yak-141 in the West. Thereafter, NATO designated the aircraft the codename Freestyle. The Yak-141 was an impressive aircraft for its time, with a maximum speed of Mach 1.4, or about 1,120 miles per hour. Its ferry range was 1,865 miles, and its service range was 1,300 miles. Its service ceiling rose to well above 50,000 feet, while its rate of climb was 48,215 feet per minute. Besides exhibiting strong qualities, pilots described a highly responsive aircraft with an outstanding fighter-like performance. Unfortunately, an incident on October 5, 1991, extensively damaged one of the prototypes. After a hard landing, the aircraft ruptured a fuel tank and ignited a fire. The pilot ejected from the cockpit after 30 seconds and was safely rescued from the sea. The aircraft required extensive repairs, so it was eventually put on display and never flew again. Later that same month, the Soviet Navy announced that there were no more funds to continue with the program. It was only a couple of months before the USSR fell, and serious rearrangements were taking place. The acclaimed model had been expected to enter production as Yak-41M, but was never delivered. In addition, plans to have improved avionics and leading-edge route extensions, or LERXs, at the wings were never brought along. Furthermore, an alternatively engined version called the Yak-43 also fell through, as did Yak-41U, a two-seat trainer that could have helped progress VTOL flight and inexperienced pilots. After announcing its inability to continue with the project, Yakovlev reached out to international partners in hopes of getting more resources to carry on. The American Lockheed Corporation, which was managing the development of their own F-35 Lightning II, took on the enterprise. Though the partnership started in 1991, Yakovlev did not make it public until a year later, and Lockheed in 1994. Prototype 48-2 was displayed at the Farnborough Air Show in September of 1992, and the then two prototype series had a last exhibition at the Moscow Air Show in 1993. Despite its potential and high expectations, the promising machine never took part in the Russian Navy. In the 1940s, the United States introduced a bomber prototype, unlike any other at the time, one using jet engines. The revolutionary plane, the Douglas XB-43 Jetmaster, was the result of several great efforts, trials, and errors. Its predecessor, the XB-42, informed the craft. However, they replaced its piston engines with two General Electric J-35 engines, boasting a powerful 4,000 force-pounds of thrust from each. Efforts to mass-produce the plane ultimately failed. Despite taking the title as the first American jet bomber, deeper issues with its design and stability killed the project, and it never served in any operational capacity. The aircraft did, however, give pilot Glenn Edwards his record-breaking speedy flight across the U.S., flying from Long Beach, California to Washington, D.C. in a mere 5 hours. The original Douglas XB-42 Mixmaster project started as a corporate exploration of how to create a fast, high-altitude attack plane. On the Air Force's side, the Air Materiel Command's military branch leaders considered the feasibility of a jet-powered bomber since October 1943. The XB-42 project seemed a promising candidate. Douglas Aircraft toyed with the initial idea of a promising twin-engine bomber aircraft designated XB-43. They showed the concept to the Army Air Force. While the military liked the proposal, they wanted the plane to be a low-cost, small project compared to the complex and considerably expensive B-29 Superfortress development program. To the Army Air Force, the possibility of an XB-43 was inexplicably tied to the performance of the B-29. Reciprocating engines powered the original prototype. However, they were placed in the fuselage, which left the laminar flow airfoil wing without drag-encouraging pylon mounts and engine cowlings. At first glance, the airframe seemed best suited to use turbojet propulsion. With the airframe complete, the United States Air Forces decided to extend its XB-42 contract with Douglas in March 1944. They requested the development of 2 turbojet prototypes designated XB-43. They also reduced their initial order on production to only those prototypes, instead of the original 13 test planes. Therefore, the XB-42's development serves as the launching pad for the XB-43 Jetmaster. The XB-42's design was somewhat revolutionary, using a cylindrical fuselage and a considerably sizable cruciform tail with a coaxial pusher propeller at the rear. Air intakes were positioned on the leading edge of the wing. The aircraft used tricycle gears while on the ground, considered unusual at the time. Likewise, the pilot and co-pilot sat in separate bubble canopies, while the bombardier sat in the aircraft's nose area. The aircraft's defense included a pair of 50 caliber machine guns that could fire forward and 4 rear-directed machine guns under the back of the plane's wings. They were controlled from the co-pilot's chair through a complex aiming system, albeit with a limited field of fire. The primary goal was to make a plane so fast it wouldn't even need to engage the enemy. A variant labeled XA-42 was designed in 1943. The design carried 16 machine guns, or 2 machine guns and a cannon. However, the model was never finished. The prototype used Allison V1710-125 liquid-cooled engines, which were located behind the crew's cabin, matched with a complex drivetrain. Each engine powered one of the plane's stacked propellers. The pusher propeller design gave the plane clean wings, which also assisted in flying at high speeds. Douglas wanted to mass-produce the aircraft. The company knew that its future B-43 aircraft could be produced quickly and rapidly, with a potential production rate of 200 planes a month. At one point, the U.S. Air Forces considered placing an order for 50 of them. However, these plans never materialized, since the US AAF was more interested in the XB-45 Tornado bomber, which would improve upon every performance aspect. While work on the XB-43 version wasn't complicated, just as Douglas predicted, it required almost 2 years to be ready for flight due to constant delays with the J-35 power plants. The delays were mostly caused by the general slowdown of the aviation industry in the US following the conclusion of the Second World War. In the meantime, the first 2 completed XB-42 prototypes had their maiden flight on May 6, 1944. Still, they did not fly with turbojets. The first turbojet bomber aircraft flew on May 17, 1946, taking off from Muroc Army Air Base, piloted by Bob Brush, with engineer Russell Thaw in the co-pilot seat. From the get-go, the aircraft had significant handling issues. The low-slung tail was cumbersome during takeoff and landing. Furthermore, while in flight, the XB-42 suffered from excessive yaw and energetic vibration. The cooling of the V1710 engines was troublesome as well. Still, the high speed worked. Issues were mostly fixed through small adjustments. Douglas aircraft waited expectantly for the arrival of the General Electric engines. Once they were installed and tested for taxing, something went wrong. During one of these tests, an engine failed horribly. The compressor blades burst through the engine casing, destroying parts of the airframe and even injuring a technician. This resulted in an additional 7 months of waiting time for repairs to be completed. The completed XB-42, under the A configuration, traveled up to 410 miles per hour and cruised at over 300 miles per hour. It could carry a payload of 8,000 pounds. Furthermore, it could fire within a range of 2,000 miles. Despite the initial setbacks and time-consuming development, the aircraft was considered a smashing success. Yet the final testing and success of the high-altitude B-29 Superfortress undermined this success, reducing the need for other planes. Since jet engine technology just emerged, and piston engine-based designs were dying out, the XB-42 was left in temporary limbo. Eventually, it was scrapped. In December 1945, pilot Glenn Edwards broke the speed of flight record using an XB-42. He flew from Long Beach, California to Washington, D.C. in only 5 hours and 17 minutes. Unfortunately, the aircraft itself ended up irreparably damaged due to gear failures soon after landing. Still, its sister craft survived and moved to test programs. For one of the tests, the aircraft was modified by the introduction of 2 Westinghouse turbojets under the clean wings. Still, they offered only 1,600 pounds of thrust each. XB-43. The XB-42 flew multiple test flights to show the capabilities and challenges of jet engine technology configured as XB-42A. Douglas aircraft managed a top speed of 488 miles per hour. However, the plane was damaged beyond repair. By 1949, the Army Air Forces removed the aircraft from its official inventory. Still, this was not the death of the design. Under the amended 1944 contract, Douglas built the jet-powered prototype XB-43, using mostly the XB-42 airframe. 2 ordered prototypes were built. One was an adapted XB-42 static test version, given the XB-43 configuration through the removal of its Allison V1710 V12 engines and their replacement with the General Electric J35 turbojets. 2 inlets were cut on each side of the XB-42 behind the cockpit. Elongated exhaust ducts were placed where the coaxial propellers once sat. Due to the lack of propellers in the design, the bottom stabilizer of the cruciform tail was removed. This last change helped in fixing the ground handling issues. The vertical stabilizer, on the other hand, was more difficult. Douglas Aircraft felt the project was promising. They pressured the Army Air Force to get a production contract for a bomber and an attack variant. Still, the military decided to take a wait-and-see position and patiently stood by while Douglas developed and tested it. The XB-43 was crucial in the development of new procedures and developments using jet engine technology. A second prototype was completed and flown on May 15, 1947. It arrived at Muroc Air Force Base in California in April 1948. This version was designated YB-43, nicknamed by personnel as Versatile 2. Its nose had clear plastic, replaced with plywood once it started cracking due to extremely high or low temperatures. To keep the plane airborne, the first XB-43 was cannibalized for the second prototype when the Versatile 2 was damaged in February 1951. Versatile 2 logged 300 hours of flight time until it was retired in December 1953. The wait-and-see position turned out to be a wise choice, since the J-35 power plants suffered frequent delays. Soon after installing them on the XB-42, one of the engines detonated, which delayed the overall program by half a year. The war ended within that time. Once the XB-43 was created, the Army Air Force opted to treat it as a test bed rather than a possible production plane. Instead, they focused their energy on the more promising B-45 Tornado, which would become the first operational jet bomber. As a result, the true first jet bomber was left without a contract, despite overperforming. Several processes, procedures, and tactics developed for the XB-43 set a precedent for future jet bombers. The hours of test flights provided valuable information for future developments as well. Some documentation even refers to the YB-43 prototype as the A-43, suggesting that there was at least some discussion around using the aircraft in an attack role. There's only one remaining model of the XB-42 and another of the XB-43. Although both are hosted at the United States Air Force Museum in Wright-Patterson Air Force Base by Dayton, Ohio, both are covered, awaiting restoration. While the aircraft did not survive the test of time, the XB-42 and 43 started a new era of aircraft development for the United States, focusing primarily on speed. It helped the Air Force and private companies develop a plan for dealing with jet aircraft operations, since the XB-43 was the first jet bomber to fly in the United States. As the Cold War started, the United States found itself deep in an ever-changing era of jet bomber developments. These bombers were significant in deterring nuclear war with the Soviet Union. When World War II ended, the US began conducting experiments with aircraft capable of Mach 1 speed at a steady pace. US engineers knew that supersonic fighters and jets were the future of aerial combat. Some designs were successful, but with technology advancing quickly with every new discovery, the US Air Force wanted to take it to the next level. With the sole purpose of getting ahead of the Soviet Union in the arms race, the rising enemy of the decades-long Cold War, the US government was focused on developing cutting-edge military-grade technology before the Soviets did. The US Army and Air Force requested aircraft companies to develop a design capable of reaching or surpassing Mach 2 and maintaining such speed. The result was the ambitious Douglas X-3 Stiletto. Produced by the renowned Douglas Aircraft Company, who gave the US and the Allies the legendary Douglas SBD, nicknamed Slow but Deadly, and the rugged A-20 Havoc, the Stiletto was a unique piece of engineering. It was the sleekest of the early experimental aircraft with supersonic speeds. It was a one-man jet, made entirely of aluminum with a very unique look never quite seen before. Nonetheless, although the long and slim fuselage had the looks to accomplish its goals, the X-3 Stiletto fell short of its performance goals. It proved underpowered to the grand idea of reaching Mach 2, as it could barely get to Mach 1. Its testing, though, gave engineers the insights needed to produce the Lockheed F-104 Starfighter. This plane had a similar trapezoidal wing and could successfully reach Mach 2 speeds easily. Today, The Douglas X-3 Stiletto is remembered for its slender look and its ambitious capabilities that distance its design from other iconic Douglas aircraft that were bulky, rugged, and built for intense combat situations. In the years leading up to World War II, the U.S. Army requested that Douglas Aircraft Company study the possibilities of creating aircraft designs capable of supersonic speed. It was 1941, and the U.S. was about to enter the war. American isolationists had put enough pressure on Roosevelt's government to refrain from joining the global conflict. Nonetheless, the embargo on Japan's expansionist empire was a disguised declaration of war that would detonate sooner than expected. With that in mind, and ever since the Japanese began that aggressive expansion in the mid-1930s, the U.S. made efforts to modernize and grow its military across all branches. The Army, Navy, Marines, and Air Corps began replacing their old equipment and fortifying U.S. territories in Asia if the Japanese decided to attack. No one expected any real threat, but they were wrong. When the Army requested that Douglas design an aircraft capable of reaching Mach 1 speeds, or supersonic fighters that could break the sound barrier, the company was already busy producing the legendary Douglas SBD, or Slow But Deadly. This aircraft would become crucial during the first year of the war, especially in the Pacific, when the U.S. was caught by surprise at Pearl Harbor. From 1941 until the beginning of 1943, the Douglas SBD would be the vanguard of the U.S. Air Corps, fighting off the Japanese Zeros in Midway, Guadalcanal, Tarawa, and the Solomon Islands campaign. Ongoing modifications made to the company's most effective aircraft, the SBD and the A-20 Havoc, kept engineers away from focusing on experimental aircraft such as the supersonic fighters. The war effort and the fate of the world came first. Sturdy and steady remained the name of the game. The company had to fulfill aircraft requests shipping overseas to the UK, France, and especially Russia. Stalin was desperate to rebuild his air forces after the furious German advance of Operation Barbarossa. In December 1943, when the tide of the war began to slowly favor the Allied nations, the U.S. Air Force requested again aircraft companies to come up with a Mach 1 aircraft. It was one eye towards the future. In January, Douglas submitted a project for approval, but the program never saw the light. It would not be until June 1945 that Secretary of War Henry L. Stimson approved Douglas's request to develop an aircraft capable of Mach 2 or more at 29,000 feet. The war had come to an end in Europe. New intel gathered from German engineers gave the U.S. valuable information for further technological advances. Besides requesting Douglas to develop their aircraft with Mach 2 capabilities, the Secretary of War established that the airplane had to fly for 30 minutes straight, take off and land under its own power. Douglas began working on an airframe powered by combinations of rocket and jet engines that could produce enough thrust to reach Mach 2. In 1947, plans changed when Westinghouse Company announced it was conducting tests on a unique afterburner-equipped turbojet called J-46. This allowed the Douglas engineers to drop the use of rocket boosters and focus solely on building their new plane around the J-46 jets. When the airframe design was concluded, Douglas and the USAF signed an agreement on June 30th, 1949. The company was going to build 2 prototypes of their Model 499D under the military designation X-3. During the first months, the team at Douglas encountered one problem that would ultimately doom the project. The planned Westinghouse J-46 engines failed to provide the power expected of their size and weight, and were deemed unsuitable for the X-3's slender airframe. They had to be replaced by J-34 engines. The J-46 would have raised the performance of the J-34 from 4,900 pounds thrust on afterburner to 7,000, which would have drastically increased overall power. The team had to make adjustments to the X-3 to fit the J-34 engines and make the most out of it when it came to performance. In 1950, the National Advisory Committee for Aeronautics made a series of recommendations to Douglas for improving the aircraft's design, which had some flaws that would lead to uncontrolled oscillations. Other difficulties led to the cancellation of the second prototype shortly after. The surviving X-3 was finished on September 11, 1952, and it was delivered at Edwards Air Force Base, California, for testing. The final design had a unique and intriguing look. It was unusually slender, with a long, sharp nose, small trapezoidal wings, and an all-metal airframe made of aluminum alloy. It was 66 feet 9 inches long, with a wingspan of 22 feet, 8.25 inches, and a height of 12 feet. The purpose behind the thin fuselage design was not about the looks, but about performance to achieve low drag at supersonic speeds. Weighing 16,120 pounds, the emphasis of the X-3 was on its speed. The almost hidden cockpit and the windscreen mitigated aerodynamic heating effects. At the same time, the small straight wings were designed for optimal speed at Mach 2. The first flight of the X-3 was on October 20th, 1952, by Douglas test pilot Bill Bridgman. He had the honor of taxiing it for the first time 5 days before, and to everyone's dismay, the unique design failed to live up to the expectations. The performance of the X-3 was mediocre at best. The X-3 had a clunky takeoff speed of 260 miles per hour. During 20 minutes of testing, Bridgman radioed Major Charles E. Yeager and reportedly told him, quote, "This thing doesn't want to stay in the air." When the demonstration exercise was done, Bridgman touched down at 240 miles per hour to keep the plane stable. In the following months, until December of 1943, Bridgman would make a total of 26 flights aboard the X-3. Things did not change much in terms of achieving better results. Despite design tweaks, the J-34 engines were always going to be underpowered, even with the addition of afterburners from solar aircraft. The X-3 reported a maximum speed of 706 miles per hour and a service ceiling of 38,000 feet. The aircraft was difficult to control, and it was underperforming in almost every aspect. The only way in which the prototype was able to achieve Mach 1 was in shallow dive. On July 28, 1953, Bridgman put the aircraft to limit and reached Mach 1.21 in a dive of 30 degrees from 36,000 feet. On October 21, 1953, one of the engines lost portions of its turbine blades during a flight test, forcing Bridgman to make a single-engine landing on the afterburner. When the contractor test program ended in 1953, the X-3 was finally delivered to the USAF. The X-3 Stiletto flew 20 times under the National Advisory Committee for Aeronautics, or NACA, and the U.S. Air Force. Lieutenant Colonel Frank K. Everest, a veteran USAF pilot, experienced firsthand the sluggish controls at low speeds of the X-3. He called the aircraft, quote, "one of the most difficult airplanes I've ever flown." NACA pilot Joseph A. Walker conducted 8 research flights aboard the X-3 during September and October of 1954. According to NASA spreadsheets, during these tests, quote, "the X-3 was abruptly rolled at transonic and supersonic speeds, but the rudder kept centered." It was during one of these tests, and the only prototype was almost lost forever. On October 27, 1954, at an altitude of 30,000 feet, Walker made an abrupt left roll at Mach 0.92. Besides the expected move, the X-3 pitched up 20 degrees and yawed 16 degrees. NASA author Yvonne Gibbs wrote that after that, quote, "The aircraft gyrated for 5 seconds before Walker was able to get it back under control." He then set up for the next test point. Walker put the X-3 into a dive, accelerating to Mach 1.154 at 32,356 feet, where he made an abrupt left roll. The X-3 reached a G-loading of minus 6.7, and then a plus 7 when it pitched upward. When Walker was able to regain control and land, a closer examination of the X-3 showed that the fuselage had been tested to its maximum load limit. The aircraft could have broken up during the maneuver. After that, the X-3 was grounded for months. Between September 1955 and May 23, 1956, Walker himself tested the aircraft again. NACA wished to understand the phenomenon of roll coupling, which occurred when a maneuver in one axis would cause an uncommanded maneuver in one or two others. After the test of 1956, the Douglas X-3 Stiletto was retired to the National Museum of the USAF at Wright-Patterson Air Force Base. Today, it can be appreciated on the museum's 4th floor as one of the first prototypes created to achieve Mach 1 and Mach 2 speeds in the age of supersonic fighters. The F-89 Scorpion was the first of its kind. It was designed as an all-weather interceptor, with the objective of shooting down Soviet nuclear bombers before they could reach the U.S. After many years of false starts, crashes, and redesigns, it ultimately found its true purpose, becoming the first aircraft armed with an air-to-air nuclear missile. This weapon would leave no doubt if it came to bringing down a fleet of Soviet bombers. The Scorpion was paired with the Genie, considered the most powerful interceptor missile ever deployed by the U.S. Air Force. It was built to be so effective in destroying enemy bombers that no countermeasure could work against it. This extraordinary weapon was only launched once during a nuclear test in U.S. territory, over the heads of 6 men that lived to tell the story. In August 1945, the U.S. Army Air Forces issued a specification for an all-weather interceptor that could replace the P-61 Black Widow. They required an aircraft with a top speed of 520 miles per hour and armed with aerial rockets that could be stored internally. The objective was to build a fighter jet that could intercept and destroy hostile aircraft under night and inclement weather conditions. One of the chosen designs was the N-24 by the Northrop Corporation. It had a slim body, a 2-man pressurized cockpit, and a conventional tailwheel-type landing gear. The first prototype flew on August 16, 1948, from Edwards Air Force Base. Soon after, its designation changed to XF-89. This initially simple aircraft faced several accidents that led to modifications over the years. When the Air Force conducted the first competitive evaluation of 3 different prototype proposals for all-weather interceptors, none of the pilots were impressed. They even graded Northrop's Scorpion low in ease of maintenance and cockpit arrangement. Disappointment ran so high that the pilots recommended developing the Lockheed F-94 Starfire as an alternative interim aircraft. However, the production of the F-89 continued because, from all the prototypes, it was the fastest and the only one considered a real fighter jet. The F-89 earned the nickname Scorpion thanks to its black color and high-mounted tail. It was a large and heavy aircraft with a distinctive main gear. In 1949, it was updated with removable wingtip fuel tanks and ailerons that acted as dive breakers. The second prototype required an almost total redesign. The new version had a pointed nose, upgraded engines, and permanently mounted wingtip fuel tanks. Instead of the black color that characterized the first model, this prototype had a natural metal finish. The XF-89A, as it was called, flew for the first time on November 15, 1949. In 1949, a prototype of the aircraft was used for the John Wayne movie Jet Pilot, which intended to show off the latest aircraft technology of the U.S. Air Force. The F-89 was used as one of the fighters shown in the last scenes of the movie. It was also one of the aircraft flown by the female protagonist in a test flight. The movie wasn't released until 1957, and by then, most of the technology shown was outdated. Shortly after its cameo, the prototype was involved in a mid-air collision with a DC-7B, which crashed into a schoolyard in Los Angeles, California. Both jets were in the middle of functional flight tests when they collided nearly head-on. On February 22, 1950, a couple of months after its inaugural flight, One of the other prototypes crashed due to a flutter problem that caused the entire tail to break off. Production was halted while engineering and wind tunnel tests were conducted to discover the cause of the crash. Northrop was able to rescue the Scorpion program by quickly modifying the engine exhaust and adding external balances that controlled the oscillations of the aircraft. The production of the Scorpion began later in 1950, and the next year it finally entered the U.S. Air Force with the 84th Fighter Interceptor Squadron Black Panthers. Although it was better than the Bravos aircraft previously used, the Scorpion was grounded for a year because of continuing structural issues with the wings and the engines. In total, 6 Scorpions crashed in 1952, and one of them in front of an audience watching an air show. A modification program was put in place to fit stronger wings into all models, which dramatically reduced the jet's accident rate. By 1954, all the F-89s had new engines and a better thrust level. This made them more reliable and allowed them to re-enter service. The definitive Scorpion was the F-89 Delta, which flew for the first time on October 23, 1959. It had the aerial rocket Mighty Mouse on each wingtip tank and a new radar. The most relevant change was that the guns on its nose were replaced with additional fuel tankage. The Delta successfully engaged with the Grumman F-6F-5K Hellcat drone. A total of 682 F-89 Deltas were produced. Some of them were used by Northrop as target drone launchers for the training crews of U.S. Army Nike surface-to-air missile sites. After several changes due to thrust deficiencies in service, 350 of the Deltas were eventually updated to the F-89J, a 2-seat jet with a radar operator to guide the pilot. It had new wings, engines, landing gear, and wing nacelles. It had an increased fuel capacity and an additional radar. This updated version of the Delta became the first jet to carry an all-rocket armament and to be equipped with up to 4 Hughes Falcon air-to-air guided missiles. The jet was able to locate and intercept any enemy aircraft during day or night, in spite of weather conditions. Even while its design is considered conventional for the time, it became truly innovative by being the first aircraft to carry the Genie, the world's first nuclear-armed air-to-air weapon. The Scorpion and the Genie were paired together for most of the early 1960s, but the weapon was only launched once. The final version of the F-89 served with the Air Defense Command as the first fighter interceptor to carry nuclear armament. Without their nuclear weapon, it later entered the Air National Guard and joined the semi-automatic ground environment air defense system. A total of 15 variants and 1,050 Scorpions were produced. Eventually, the F-89 was replaced by more modern aircraft like the F-4 Phantom and the Convair F-102. However, it is remembered for being the main U.S. air defense interceptor during most of the 1950s, and for never firing a shot in anger. The F-89 was equipped with the aforementioned Genie, considered the most powerful interceptor missile that has ever been deployed by the U.S. Air Force. The Douglas Aircraft Company began developing the weapon, codenamed Ding Dong, in 1954. The objective was to build an unguided nuclear air-to-air weapon that could work against massed formations of high-speed bombers. The MB-1 Genie was introduced to the U.S. Air Force in 1957. It was armed with a 1.5 kiloton nuclear warhead with a time-delayed detonation. It also had a flight time of 12 seconds that allowed it to cover over 6 miles. Its powerful motor enabled it to attack any aircraft that moved at high speed and altitude. The Genie would be extremely effective at destroying enemy targets, possibly even an entire bomber formation, thanks to its blast radius of almost 1,000 feet, and due to the fact that no countermeasure helped to avoid it. To safely escape after launching the warhead, the F-89 had to pull away in a sharp turn, which was a tricky maneuver to achieve with the aircraft. However, the timer for the aiming and detonation of the Genie would not begin until the rocket motor burnt out. This gave the aircraft enough time to run away from the blast radius. The rockets were carried for the first time by 15 F-89 interceptors deployed at Air Force bases in Michigan and outside San Francisco. Over 1,000 Genie rockets were produced until 1962. During this time, the rocket was only detonated once, during Operation Plum Bomb. It was later packed with tiny bomblets and converted to a conventional weapon capable of blowing up targets on the ground. In the 1970s, it was upgraded with a longer-lasting motor and then removed from the inventory a decade later. Interest in air-to-air nuclear missiles was short-lived. It was soon decided that launching a nuclear weapon required the approval of several high-ranking authorities in the White House and couldn't rely solely on a pilot's decision, which added unnecessary bureaucracy. Also, conventional air-to-air missiles were more reliable, and after the development of ballistic missiles, there was no need to carry nuclear weapons aboard planes. Operation Plum Bomb consisted of a series of controversial nuclear tests in the Nevada desert. The operation had several objectives, like conducting biomedical experiments, running safety tests, and improving weapons design. One of the most shocking tests, under the codename Shot John, was meant to prove to the American public the alleged safety of a low-grade nuclear exchange in the atmosphere. On July 19, 1957, 5 Air Force officers volunteered to stand under the detonation of a Genie rocket launched by an F-89 Scorpion. George Yoshitake was the Department of Defense photographer that filmed the event. He didn't volunteer like the other 5 men, and instead thought the job consisted of documenting the nuclear test from a distance. The night before his task, he found out he would actually be standing below the blast zone without any protective gear. In an interview with the Huffington Post, he recalled, quote, "I had a baseball hat, and I put that on, just in case." Wearing only their summer uniforms, the officers stood on a spot marked as Ground Zero, Population 5. A little after sunrise, the F-89 fired the almost 2-kiloton warhead, 1/8 the size of the A-bomb dropped on Hiroshima. The explosion occurred at an altitude of 18,500 feet and ignited a bright light that shortly blinded the officers. Cameraman Yoshitake remembers that after the detonation, the officers congratulated each other on still being alive. One of them even passed around some cigars. The 6 men lived past the 1990s, and there's been no evidence of long-lasting effects on them after the detonation. However, in an interview with CBS, Yoshitake said that all of them were diagnosed with cancer at some point in their lives after the test. Convair's XB-46 prototype has been described as one of the most beautiful-looking jets of its time. It had a sleek, straight-wing design and an innovative pneumatic control system. The jet also had a weapons load capacity of up to 22,000 pounds. The XB-46 prototype for a jet-powered bomber was a powerful sight to behold. The Needle, as its test pilots nicknamed it, was initially designed to counter the German Arado AR-234, the world's first operational jet-powered bomber. But neither luck nor history was ever on this Convair's prototype side. The bomber never saw production or active duty. The Needle never moved on from the testing stage, as it was largely overshadowed by what later became one of the most popular bombers of the mid-century, Boeing's Stratojet. Though short, its legacy still lives on, and its design served as an example for other bombers of the post-war era. As budgets shifted, a new priority emerged in its place, one of Convair's most bizarre creations, the forward-wing swept XB-53. As the German strength diminished in the later stages of World War II, innovation in combat aircraft was one of their final attempts at achieving air superiority. This led to the development of the Arado AR-234 Blitz. It was the world's first operational jet-powered bomber and the last Luftwaffe aircraft to fly over England during the Second World War. First introduced in September of 1944, the Blitz was so fast it could outfly most ground-based defenses and airborne interceptors. It was nearly impossible to intercept and excelled in covert reconnaissance missions before being converted to a light bomber role. The U.S. Department of War was aware of the damage this German technology could inflict on their bases. It was almost mythical when it first appeared. Few in Europe had heard or seen turbojet engines. Allied group intelligence documents warned of their existence, but Allied sightings were few and far between, even though over 200 of the Blitzes had been built. It's no wonder. The AR-234 was one of the fastest planes of the war, reaching 540 miles per hour. The Americans were thus determined to make their own American version of a jet-powered bomber to compete. It would pack a far bigger punch than its German counterpart, which could carry only 3,300 pounds of bombs on external racks. That same year the AR-234 was introduced, the War Department issued a new request for a medium bomber design. Boeing, Convair, Martin, and North American Aviation were the most notable responses to the initiative from the U.S. Army Air Forces for a high-flying jet-powered bomber capable of a 1,000-mile range and having a large payload. This competing group of designs came to be known as the Class of 45. Other designs from this competition included the North American XB-45, the Martin XB-48, and what eventually became the American strategic bomber of choice, the Boeing B-47 Stratojet. With World War II still wreaking havoc all over Europe and the Pacific, a mock-up of the Convair proposal, the XB-46, was approved at the beginning of 1945. A contract for 3 other prototypes was granted in the following months. The XB-46 was a simple but elegant design. Even in the years after its eventual cancellation, it's considered one of the most beautiful jets of its era. It was a straight-wing configuration, equipped with Fowler flaps that extended over 90% of the span in 4 different sections. Each wing had 5 spoilers made of magnesium. The fuselage had a sleek and aerodynamic design, which helped improve the speed of the jet. The bomber carried a crew of 3. The pilot and co-pilot were seated together under a canopy with great vision out of the cockpit. The nose section held the bombardier behind a plexiglass nose cone. The XB-46 had the first ever all-pneumatic aircraft. The new system would operate the bomb bay doors, the brakes, and the landing gear. The jet was praised for this system, which saved considerable weight and allowed a faster activation than more common hydraulic or electrical control systems. The J-35 engines installed in the prototype would later be exchanged for the improved General Electric J-47 engines. In battle, the aircraft would be able to carry a warload of up to 22,000 pounds. There were also plans to introduce a twin gun at the tail with 50 caliber heavy machine guns. Unfortunately, for numerous reasons, the XB-46 never moved past the prototype stage. By the time it entered the testing stage, World War II was over. The race for air superiority against the Germans was no longer a priority for the US Army Air Force. This resulted in the cancellation of several projects due to budget cuts. This shift in budgeting priorities severely affected Convair. At the beginning of 1945, the United States Army Air Force was interested in two of their proposals, the XB-46 bomber jet and the XA-44 CO attack jet. But there was an insufficient budget to fund both of the projects, and company officials had to decide which one was more important. Some argued that the XA-44 CO's unusual forward wing design was too risky. There was already a lot of competition for the jet-powered bomber project in which the Needle was competing. In June 1946, the USAAF agreed to fund the XB-46. The prototype made its maiden flight on April 2, 1947, at the hands of pilots Sam Shannon and Bill Martin. It was quickly nicknamed the Needle. The initial test results were mostly positive. Convair and Army Air Force pilots praised the bomber for its handling qualities. The Needle reached a maximum speed of 450 miles per hour, with a cruising speed near 440 miles per hour, a range out to 2,870 miles, and a service ceiling of up to 40,000 feet. Although its stability and control exceeded expectations during its test flights, it still needed improvements. When tensions between the US and the USSR arose, the beginning of the Cold War prompted the US Army Air Force to continue the pursuit of an operational jet-powered bomber as soon as humanly possible. Therefore, they decided to skip the competition ordinarily held between the admitted proposals. An examination was made of the designs already available to find out which one could be built faster. The only ones near completion were Convair's XB-46 and the North American Aviation B-45 Tornado. The US Army Air Force needed to pick one of them for immediate production soon. Other proposals, such as Boeing's XB-47 and Martin's XB-48, were still years behind in development. The Army Air Forces delayed their consideration for them until after they were flown. Still, there remained a slight possibility of production for these delayed prototypes. If one of these designs happened to be superior to the Convair or North American Aviation prototypes, they would re-enter consideration. Boeing would later pounce, but for a time, it was between Convair and North American. And according to the US Army Air Force's conclusions, the performance of Convair's Needle was inferior to North American's B-45 for several reasons. The Needle was larger, yet its small fuselage wouldn't be able to hold all the required radar equipment needed for a bomber. Its sleek, classy design was ultimately its demise. North American's B-45 Tornado's configuration was quite similar to other aircraft of the era, presenting fewer risks. And so, on August 2, 1946, the USAAF officially announced the production of the Tornado, and every chance the Needle had at being produced disappeared. Still, the Army Air Force didn't end up building very many B-45s at all. When the Boeing B-47 finally took its first flight on December 17, 1947, it proved to be the best of all proposals, and plans changed once again. Better known as the Stratojet, the Boeing B-47 eventually became one of the Air Force's signature jets for many years, with over 2,000 airframes being built. The Stratojet design was extremely adaptable. It was modified to perform numerous other roles and functions, aside from the bomber role. It flew photographic reconnaissance, electronic intelligence, and even weather forecasting missions. Although it was never actually used as a bomber in a mission, the Stratojet remained in service as a reconnaissance jet until 1969, becoming one of the Air Force's most legendary planes. The Convair XB-46 program was officially cancelled in August 1947. It had become outdated even before the testing was completed. Overall, the single XB-46 prototype made 64 flights and spent over 100 hours in the air. The rapid pace of aeronautical progress and the changing times quickly rendered it obsolete, as often happened in the post-war era. Even the USAAF rebranded itself in 1947, becoming what is now the United States Air Force. In July 1950, after sitting in a warehouse for a year, the Needle was flown one last time to Eglin Air Force Base. Its acclaimed pneumatic system was tested in the sizable climatic facility under the most extreme weather conditions. The XB-46's development helped improve the art of designing and flying large aircraft. Sadly, it's not possible to find it displayed in an aviation museum. The only Needle to ever exist did not survive as a whole. On January 13, 1951, the nose section alone was sent to the U.S. Air Force Museum at Wright-Patterson Air Force Base, Ohio. The rest of the Needle was scrapped in February 1952. Today, the Needle's legacy only lives through photographs, videos, and official Air Force records. Although the Needle was a decent design concept that flew relatively well and was loved by its test pilots, the XB-46 was eclipsed by a better, more adaptable airplane. The program that Convair would instead focus its efforts on, the XA-44, ultimately fared even worse. Eventually renamed the XB-53, it had erratically forward-swept wings at an angle of 30 degrees. On paper, it could reach speeds of 580 miles per hour while carrying 40 rockets and 12,000 pounds of bombs. But paper was as far as the design would get. 2 prototypes were ordered, but neither were ever built.